Assalamualaikum and hi to everyone and to our lecturer Dr. Muhammad Afzal Nizam bin Muhammad Rosli. So today we want to present one of the chapter in Thermodynamics 2, which is power plant, and this is our group member from group B. In this presentation, we have 4 contents, which is introduction, basic cycle description, actual Rankine cycle, and efficiency improvement power cycle. So we begin with introduction.
So today I am going to talk about the introduction of the history of power plant. So the history of power plant we can spread to the 5. Firstly is the early discoveries. The early discovery is the journey of the begin with the Englishman Stephen Gray demonstrated of electrical conduction in the 1740s. This led to events like a glass friction generator and batteries by Benjamin Franklin and Alasdair Volta. Second is the electric motor and generator. In 1832, Michael Faraday and Joseph Henry invented a primitive electric motor, and in 1831, they demonstrated the principle of the generator, laying in foundation for modern power system. Frenchman Hippolyte Fixie created the first rudimentary dynamo in 1832, and Antonio Pacinotti improved it for a continuous direct current DC power by 1860. Third is the Zenobie-Gramme dynamo. In 1817, Belgian inventor Zenobie-Gramme developed a dynamo that produced steady DC power. The discovery fueled enthusiasm about electricity potential. And next is Thomas Edison Central Power Station. In 1882, Thomas Edison established the Pearl Street Station in New York City, the world's first full-scale central power station. And last is the hydropower. The first hydroelectric project powered in a single lamp in England, Crescent Country House in 1878.
Rankine cycle describes the operation of steam heat engines commonly found in power generation plants as schematically shown here. In such paper from WIT's Transaction on State of Art of Science and Engineering, power is generated by alternately vaporizing and condensing on working fluid. In many cases is water, although refrigerants such as ammonia may also be used. There are 4 processes in the Rankine cycle, each changing the state of the working fluid. These states are identified by the number in figure given. Firstly, process 1 to 2s. First, the working fluid is pumped ideally isentropic from low to high pressure by the pump. Pumping requires a power input, for example, mechanical or electrical. Next, process 2s to 3. The high pressure liquid enters a boiler where it is heated at constant pressure by an external heat source to become a saturated vapor. Common heat sources for power plant systems are coal, natural gas, or natural power. Process 3 to 4s. The saturated vapor expands through a turbine to generate power output. Ideally, this expansion is isentropic. This decreases the temperature and pressure of the vapor. Lastly, process 4s to 1. The vapor then enters a condenser where it is cooled to become a saturated liquid. This liquid then re-enters the pump and the cycle repeats.
Okay, now we move to the part actual Rankine cycle. In the real situation, actually both water pump and steam turbine do not operate isentropically, or in other words, without entropy change. For a turbine, we can see the actual work output is less than the work output of an ideal process. But for a pump, the actual work input is greater than the work input of an ideal isentropic process. And we can see from the formula efficiency turbine, work actual divided by work isentropic. But for the formula efficiency for compressor, we can see is equal to work isentropic divided by work actual. And for the thermal efficiency for the Brighton equal to work net actual divided by Q in actual. Okay, to go more detail, I have example question. If we can see for the example question, given efficiency for compressor and efficiency for turbine, and the question want to ask find the temperature exit at the compressor and the turbine. For this question, we have to separate state 1, state 2, state 3 and state 4. But for the state 2, we have the state 2 for isentropy and stage 2 for the actual. Same like stage 4. We have for S and for A. when we got all the value LTP1, LTP2, enthalpy3, enthalpy4, we have to find the backwork ratio. The formula for backwork ratio is the work compressor in actual divided by work turbine out actual. And when we got the value of the backwork ratio, we have to find the thermal efficiency. The formula for thermal efficiency is the work net actual divided by Q in actual.
Next, we move to efficiency improvement power plant. So as you can see, we have 4 improvement, which is lowering the condenser pressure, superheating the steam to high temperature, increasing the boiler pressure, and Rankine cycle with reheat. We begin with lowering the condenser pressure. This chapter discusses lowering the condenser pressure as one of the methods to improve the thermal efficiency of the Rankine cycle used in steam power plants. Here are the key points regarding lowering the condenser pressure. In summary, lowering the condenser pressure as much as practically possible by using colder cooling water or operating under vacuum increase the Rankine cycle efficiency in a steam power plant by reducing the low temperature limit. However, there are practical limits on how low the pressure can be lowered. Next, we move to superheating steam to high temperature. This chapter discusses superheating the steam to high temperature as another method to improve the thermal efficiency of the Rankine cycle in steam power plants. Here are the key points regarding superheating. In conclusion, superheating the steam allows utilizing higher average heat addition temperature, directly increasing the cycle efficiency while also improving the steam quality at the turbine exhaust. But it is limited by maximum temperature constraints of material.
A good day to you, sir. Now I'll be continuing on 2 methods to improve the efficiency. Well, the first one is increasing the boiler pressure. Increasing the boiler pressure raises the temperature at which the boiling takes place. This results in a higher temperature at source for the same temperature at sink. But as you can see here, at state 4 prime, it shows that the steam quality is lower compared to the state 4. This shows that more wet steam at the turbine exhaust is expected. This may result in cavitation of the turbine blades at low pressure stages. Consequently, the efficiency will be decreased and the cost of maintenance will be increased. Therefore, we came out with another method to improve the efficiency, which is Rankine cycle with reheat. As you can see here, the moisture content at exhaust of turbine should not be more than 10%, as it can result in physical erosion of the turbine blades. However, as higher boiler pressure are required for higher efficiency, it leads to higher moisture content at low pressure stages. Thus, the steam can be reheated between the 2 turbine expansion stages to improve the turbine exhaust steam conditions. But I can see here the advantages of using Rankine cycle with reheat. This arrangement provides high steam quality at turbine exit. Therefore, for a given temperature at source, efficiency increases without reducing the steam quality at the turbine exit. Rankine cycle with regeneration. Added heat source should be high temperature as temperature at source. Heat rejected, which is temperature at sink, heat source at sink, should be less than temperature at sink. In such configuration, the Rankine cycle is provided with feed water heaters (FWH) to heat the high pressure subcooled water at the exit of the turbine, at the exit of the pump. So we will go to the feed water heaters. There are 2 types of feed water heaters: open FWH and closed FWH. For open FWH, where the two streams of high temperature steam and low temperature water mix in an open heater at constant pressure. Whereas for the closed FWH, a heat exchanger is used to transfer the heat between the 2 streams without mixing the streams. Advantages of using heat regeneration. Obviously, it improves the cycle efficiency, but besides that, it provides it removes the air that leaks at the condenser to prevent the corrosion. As we can see before, the method used before, it causes corrosion, but this, it does not. The third one, it also helps to control the large volume flow rate of the steam at the final stages of turbine. So I can conclude here that steam power plants play a crucial role in a global energy landscape by converting thermal energy fuels into electrical energy efficiently. These plants have several key components, including boilers, steam turbine, generators, condensers, and pumps, each of them contributing to an overall process of electricity generation. That's all from our group. Thank you.